Hello friends, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University. And this is our second session in the series of vectors. And in the last session, we had covered concepts like what is a scalar quantity, what is a vector quantity, what are direction ratios, direction cosines. Also, we learned about the concept like co-initial vectors, co-planar vectors, co-linear vectors. We learned about the triangle law of addition of vectors, parallelogram law of addition of vectors, and solved a lot of numericals. Now, in this session, we are going to extend our understanding and discussion towards some more concepts. Likewise, in this session, we are going to understand about dot products. In the subsequent session, we will be understanding about the cross products. What are dot products, cross products, you will be understanding. And we will be also covering vector triple products and scalar triple products. So let's start the session. The objectives of today's session is that after going through this session, you will be able to define the scalar product or dot product of the vectors. Apart from this, you will be able to find the angle between the two vectors and find projection of the vectors on another vector. So what is a scalar product of two vectors? Say we are given two vectors, say one vector A and B are there. Now vector A is subtending say angle theta on vector B, then you can by understanding of the earlier sessions, then A cos theta will be the projection of vector A on vector B. So as a result of which the dot product of the vectors A dot B will be given by magnitude of A vector into magnitude of B vector into cos of theta. Now this entity, this part, that is dot product, that is A dot B, this is the scalar product of two vectors. Scalar product of two vectors. And we are going to discuss this concept in detail. Now, if we rearrange this equation, equation number 1, you can always get that the angle between the two vectors A and B, where theta is the angle subtended by vector A on vector B, will be given by vector A dot B vector divided by magnitude of A vector to magnitude of B vector. So this is the formula, and I hope you understood that what are vectors, what is a dot product. So it is actually the projection of one vector onto another vector, and there are some of the important observations about the two vectors, that the dot product A dot B will turn out to be 0 if both A and B are not 0, if A is not equal to 0 and B is not equal to 0, but A dot B is equal to 0, this implies that angle between the two vectors is 0. That means two vectors, the angle between the two vectors are perpendicular, because A dot B is equal to magnitude of A into magnitude of B of cos theta. So when theta is equal to 90 degree, then that means A vector is in this direction and B vector is say in this direction, and the angle is 90 degree, then cos 90 degree is 0. Cos 90 degree is 0. As a result of which A vector dot B vector is equal to magnitude of A vector into magnitude of B vector into cos theta, where theta is equal to 90 degree, will turn out to be 0. Now, this is the first important observation, that if we want to prove or verify that whether the two vectors are perpendicular or orthogonal to each other, then simply we need to check that whether their dot product is turning out to be 0. If the dot product is turning out to be 0 and both vectors are not 0, then obviously these vectors are perpendicular. We will be exploring these concepts when we are going to solve the numericals. The another important observation is that if we are having a vector A, then the dot product of vector with itself will be given by A dot A, and that means both vectors are in the same direction. Since both vectors are in same direction, so theta will be equal to 0, and we know that cos 0 is equal to 1. So in that case, the formula for A vector dot A vector will resolve to magnitude of A vector into magnitude of A vector into cos of 0. That is magnitude of A vector square. So this implies that magnitude of A vector is nothing but the square root of dot product of the two vectors of the vector A. So that means A dot A, the vector product, dot product of the vector A with itself, and square root of this will represent the magnitude of that vector, and this is very much explained over here that square root of magnitude of A square is nothing but square root of A vector dot A vector. So now we are going to understand something more about the concepts of the vector. That say we in the earlier session we learned about that the unit vectors I, j and k, and we learned that say in a three-dimensional system we are having the coordinates x, y and z. Then I is the unit vector along x-axis, j is the unit vector along y-axis, and k is the unit vector along z-axis. And the angle in between x, y and z is respectively 90 degree each. So extending the learning that cos 90 degree is always 0. Therefore, if we are going to find the values of say I dot j or j dot k or k dot I, then the angle between these unit vectors I dot j is 90 degree, j dot k the angle is 90 degree, k dot I the angle is 90 degree, as a result of which these value will turn out to be 0. And this is the very important property, and we are going to use this property when we are going to solve ample number of numericals. Next observation is if I is dot product of I is taken with the dot product of I, that is the unit vector along x-axis, and then this implies theta is nothing but 0, because the vector is along the same direction, so theta is equal to 0, and we know that cos 0 is nothing but 1. Therefore, I dot I and j dot j and k dot k, that is the dot product of the vectors in the respective direction with themselves only, is equal to 1, and this is the second important observation. We learned about the component forms of the vectors, and we learned that a vector in the component form can be expressed as a1i plus a2j plus a3k. Similarly, b vector can also be expressed as b1i plus b2j plus b3k, which is expressed over here. Then the dot product of the two vectors, that is a vector dot b vector, will be explained by this expression. That means we are multiplying a vector by b vector. For the sake of better understanding, let me rewrite the equation for your understanding. You can say that a dot b can be expressed as a1i into b1i plus b2j plus b3k. Similarly, a2j into b1i plus b2j plus b3k. Similarly, a3k to b1i plus b2j plus b3k. So we multiplied each component of vector A with the vector B, and we got this as an expression. And we know that I dot I, only I dot I and j dot j and k dot k are equal to 1. Rest all the things like I dot j or j dot k or k dot I all turns out to be 0, because angle between I and j is 90 degree. We learned that the angle between unit vector I and unit vector j is 90 degree. The angle between j and k is 90 degree. Angle between k and I is again 90 degree, and cos 90 degree is 0. Therefore, all the multiplications, that is multiplication of I with j, I with k will vanish, j with I, j with k will vanish, k with I and k with j will vanish. So what will remain is only a1 b1, because I dot I is 1, j dot j is 1, and k dot k is 1. So only factors, only the values a1 b1, a2 b2 and a3 b3 will exist. So that means if we are having the vectors in the component form, that is a1 I plus a2 j plus a3 k, and b vectors such that b1 I plus b2 j plus b3 k, then the dot product of the vectors will be only given by the multiplication of the I components, j component and k component of the two vectors respectively. Likewise over here, it is a1 b1 plus a2 b2 plus a3 b3. I hope you understood that what is the representation of scalar product in the component form. Now let's solve some numerical. Now over here, a vector A is given to us in the form say 2, 3, 4, and this is actually we are expressing it in the component form 2i plus 3j plus 4k, and we are given vector B which is in the which is given in this form, and this is nothing but 1i minus 1j plus 5k. So in the component form, this is the representation, and we know these properties. These properties are say I dot I is equal to j dot j is equal to k dot k is equal to 1. But other things like I dot j dot k dot I, all are 0 because the angle is 90 degree. And over here the angle is 0 degree. So as a result of which, applying the component form, we learned that A dot B will be equal by A1 B1 plus A2 B2 plus A3 B3, where A vector is nothing but A1 I plus A2 J plus A3 K, and B vector is nothing but B1 I plus B2 J plus B3 K. So multiplying these components A1 with A2, A1 B1, A2 B2, A3 B3, from this equation you can say that we are multiplying I components, J components and K components. So that is 2 into 1, 3 into minus 1, 4 into 5. So 2 into 1 is nothing but 2, 3 into minus 1 is nothing but minus 3, and 4 into 5 is nothing but 20. And this solves to value 19. So the A dot B results to 19. Now there is an important observation about the sign of the scalar product. That means by observing at the sign of the scalar product, can we determine that what is the angle between the vectors, that the angle is either acute or obtuse. So we know the fundamental definition of the scalar product, that A dot B is equal to magnitude of A into magnitude of B cos of theta. Now the important observation is that if A dot B is greater than 0, then obviously the cos theta is to be greater than 0, and that means the theta is acute. If A dot B is equal to 0, that means vector A and vector B are perpendicular to one another. Vector A and vector B are perpendicular to one another, as a result of which the angle is 90 degree and cos of 90 degree is equal to 0. So that means the theta is right angle and cos theta is equal to 0. In this situation, we need to have the observation that vector A should not be equal to 0 and vector B should not be equal to 0. But if A dot B is equal to 0, this implies cos theta is equal to 90 degree, and this implies cos theta is equal to 90 degree. So that means it is right angle. If A dot B is less than 0, if A dot B is less than 0, that means the angle is obtuse and cos theta is less than 0. So that means by looking at the sign of the dot product, we can always find that what is the angle and what is the status of the angle. Now there are some of the important properties. First and the most important property, that scalar product is commutative in nature. Commutative property says that A dot B is equal to B dot A. Similarly, we also learned in the last session that if vector B is in this direction, then if the direction is reversed, then the vector will be minus B, or minus B will be having the direction opposite to that of the vector B. So A dot minus B will be given by, can be rewritten as minus of A dot B. And apart from this, we can also say that minus of A vector into minus of B vector is always equal to A vector dot B vector. So this identity holds, and for every pair of the vectors A and B. The third important property is that if we are having a scalar component lambda and lambda 1, say it be multiplied by vector A, and we are having a scalar component lambda 2 and multiplied it by vector B, and we take the dot product of the two, then the result will be equal to lambda 1 into lambda 2 into A dot B. We are going to use these properties when we are going to solve the numericals. The lambda 1 and lambda 2 are the scalar components, whereas A and B are the vector components. The distributive property holds for the dot product, which says that if we are having a vector A and we take the dot product of vector A with the sum of the two vectors B and C, then it is equivalent to vector A dot B plus vector A dot C. So this is nothing but the distributive property, and we already learned that if I, j, k, which are the mutually perpendicular unit vectors, then we are having two observations, that I dot I is equal to j dot j is equal to k dot k is equal to 1, whereas I dot j or j dot k or k dot I will turn out to be 0, because theta is equal to 90 degree and cos 90 degree is equal to 0. Now let's extend our discussion to one more topic, that is angle between the two vectors. Say we are having two vectors, vector A and vector B, and let theta be the angle subtended in between the two vectors, and we learned that the dot product of the two vectors is given by magnitude of vector A into magnitude of vector B into cos of theta, and we learned that we can determine the angle between the two vectors by rearranging this equation, wherein we can get that A dot B will be equal to magnitude of A into magnitude of B, and we can determine theta is equal to cos inverse of vector A dot vector B upon magnitude of vector A and magnitude of vector B. And we learned that in our earlier discussion that vector A is equivalent to square root of A dot A. Similarly, vector B is also equivalent to square root of vector A or vector B dot vector B. So, using these expressions in place of A and in place of B, you can always get this expression. So, this is the dot product. So, if we are given the two vectors A and B, then cos theta can be expressed by this formula, can also be expressed by this formula, and we can determine theta by this formula. So now let's solve one numerical. We are given two vectors A and B. That means vector A is nothing in the component form is 3i plus 4j, and vector B is expressed as 1i plus 2j. So these are the component form representation of the vectors A and B, and we know that that the dot product in the component form will be given by A1 B1 plus A2 B2. Because we are only having two vectors, if there is three-dimensional space, then the dot product A dot B in the component form will be given by A1 B1 plus A2 B2 plus A3 B3. So multiplying the A1, this is A1, this is A2, this is B1, and this is B2. So that means A1 into B1 is nothing but 3 into 1, and A2 into B2 is nothing but 4 into 2. solving, you get the expression A dot B is nothing but 11. Vector A dot B is equal to 11. And we also learned in our earlier sessions that if we are given a vector A in the form say xi plus yj, then magnitude of A will be given by square root of x square plus y square. Applying this understanding, we can find the magnitude of vector A. A vector is given us as 3i plus 4j. Therefore, magnitude of A will be equal to square root of 3 square plus 4 square. So, this is the magnitude of vector A, which turns out to be 9 plus 16, that is square root of 25, that turns out to be 5. So, 5 is the magnitude of vector A. Similarly, you can find the magnitude of vector B. The vector B given to us is 1i plus 2j. Therefore, the magnitude of vector B should be equal to square root of 1 square plus 2 square, that is square root of 5, which turns out to be 2.236. And we learned that cos theta is equal to A vector dot B vector upon magnitude of A vector into magnitude of B vector. In the above cases, we already found that magnitude of A is 5 and magnitude of B is 2.236, and we also determined A dot B to be 11. Substituting the values, you get the answer 0.938. That means theta is nothing but cos inverse of 0.938, which turns out to be 10.47 degree. Now, another important concept is the projection of one vector on another vector. We learned that say A and B are the two vectors, say A vector and B vectors are there, and theta is the angle which is subtended by vector A onto vector B. Then we learned that the projection of vector A on B will be given by this is the projection. So this projection will be equal to magnitude of A cos theta. So this projection will be given by A cos theta into B vector. So, and this will be simplified because we learned that the B vector is equal to magnitude of B into B unit vector. So, simplifying this expression, you will get that A dot B upon magnitude of B into B unit vector, and which can be simplified to A dot B into B vector upon B magnitude of B square. So, you can simplify this by simple arithmetic. Now, the scalar component of projection of A on B will be given by A dot B upon B, whereas the component of projection of B on A will be given by A dot B by A. So, whatever is turning at the letter A on B, so B should be here. B on A, so A should be here. So, A dot B by A is projection of B on A. Projection of A on B is A dot B by magnitude of B. So, let's solve one numerical. Now, over here 2 vectors are given to us. Vector A is 3i plus 4j and vector B is 1i plus 2j. For the sake of simplicity, we are just taking the 2-dimensional system. Therefore, the A dot B, vector A dot B will be A1 B1 plus A2 B2, and which turns out to be 11. Now, we know the formula for projection. It is A dot B upon magnitude of B square into B, which we got this. This is the formula which we are referring. Now, this is the formula. So, in this formula, the first component is A dot B, and we determined A dot B as 11. Second component is magnitude of B square. So, magnitude of B square will be equal to, because this is this, so this implies magnitude of B will be equal to square root of 1 square plus 2 square. This turns out to be square root of 5. So, magnitude of B is this. So, magnitude of B square will be equal to 5, and which is this. And we need to have the vector B, and vector B is nothing but 1i plus 2j. So, substituting the values, we got the answer 11 by 5 into 1i plus 2j. So 11 into 1, that means you will be having 11 by 5I plus 11 into 2 is 22, so 22 by 5J, and this turns, by solving this you will get it equal to 2.2I plus 4.4J. So this is the value of the projection of. Now we are having another example wherein we are going to explore the properties which we had learned in the beginning of this session. Now this question is show that magnitude of A into B plus B into magnitude magnitude of B into A is perpendicular to magnitude of A into B vector minus magnitude of B vector into A vector for any non-zero vectors A and B. So A vector is not equal to 0, B vector is also not equal to 0, and we are supposed to prove that these two vectors are perpendicular. So if these two vectors are perpendicular, then obviously their scalar product, that is their dot product, should be 0. So you can say that there you need to find their dot product. So dot product is this, that means this is, say, first vector, and we are taking the dot product with the second vector. So simply by opening the braces first into this complete vector and this second component into this complete vector, you can write it magnitude of A into B vector into the second complete vector plus magnitude of B into A vector into the second complete vector. Now again opening the braces, magnitude of A multiplied by magnitude of A, so you will be getting magnitude of A square, and the second part will be B vector dot B vector. So we opened the braces, and we the second expression will turn out to be A magnitude of A into magnitude of A into magnitude of B into B dot A. So B dot A will be this is the next term. Opening the braces, again you will be getting magnitude of A, magnitude of B into magnitude of A into A dot B minus magnitude of B square into A dot A. So this is how we are going to open the braces. And we know that the property is A dot B is equal to B dot A. And we also know that A dot A is equal to magnitude of A square and B dot B is equal to magnitude of B square. Now using these properties, you can see that this is A dot B dot A, this is A dot B, and so these two terms will cancel out. Secondly, A dot A is magnitude of A square and B dot B is magnitude of B square. So again we are having these two terms, this term and the last term, they are of the opposite sign. We are having magnitude of A square into magnitude of B square, and the last term will be magnitude of B square into magnitude of A square. So they will also cancel out, as a result of which the final result is 0. So simply we explored the properties of the dot product, that is the scalar product, wherein we learned that A dot B is equal to B dot A. Also we explored the property that A vector A dot vector A is nothing but magnitude of vector A square, which is this property, and B dot B is nothing but magnitude of B square. Using these properties in the expanded form of the dot product of the given two vectors, we find that all the values cancels each other, as a result of which the result turns out to be 0. Now one more example is there. This example requires that show that the diagonals of the rhombus are at right angles. So just look at this figure. Say the A, B, C, D is a rhombus, wherein AC and BD are the diagonals, and we are supposed to prove that this angle is 90 degrees. So there are two important properties to remember. First is a rhombus is a type of parallelogram where all sides are of equal length. So all sides AD, DC, BC and AB all are of equal length. Second is diagonals of rhombus bisect each other. So bisection, they divide into the equal values 1 into 1, 1:1 they are dividing. So, by looking at the figure, you can always see that AC, vector AC, applying the triangle law of addition of vector, is nothing but AB plus BC. So, this is equal to AC. And you can always see that BD vector BD is, you can say that this is that vector AB. So, applying the triangle law of addition of vector, you can always say AB plus BD, vector AB plus BD is nothing but vector AD. So, this implies vector BD, because we are interested into the diagonals. So, that is why we are exploring BD. But as per the triangle law of addition of vector, the first vector is AB and second vector is BD. So, the resulting vector will be AD. So, by applying the triangle law of addition of vector, AB plus BD should be equal to AD, but we are interested in BD because BD represents a diagonal. So, BD is nothing but AD vector minus AB vector, which is this. Now, taking the dot product of the two vectors, that is AC and BD, and AC and BD both represents the diagonals of the rhombus. So, AC dot BD will be given by AB plus BC, which is this equation, and AD minus AB, AD minus AB. And you know that BC is equal to BC, this BC is equal to AD because they are parallel, and rhombus is a type of parallelogram and all sides are equal. So, that means the two vectors are parallel to one another. So, we can replace BC by AD. So, we can replace BC by AD because BC is equal to AD, as a result of which this equation will get modified to AB plus AD dot AD minus AB. Now, this is, we are exploring the identity that A square minus B square is nothing but A plus B into A minus B. Applying this identity, you got the answer AD square minus AB square. Now, what is AD? AD square minus AB square. So, square of AD is equal to square of AB. So, that because all sides are of equal length. So, all sides are of equal length. So, AD will be equal to AB, as a result of which the difference between the two, that is AD square minus AB square, can be expressed as AD square minus AD square. This turns out to be 0. Since the dot product of AC and BD is turning out to be 0, that means vector AC and vector BD are perpendicular to one another, and this proves that the diagonal AC and BD are perpendicular to one another. So, I hope you learned that how to explore the properties of dot product to solve the problems, and we, in this session, we learned something about the dot product and how to apply the properties of dot product to solve the numericals. I again advise you to go through the self-learning material and try to solve more and more problems. This will help you out for the better understanding. Thank you.